Good morning, children. This is lecture 5 of chapter Chemical Kinetics. In this lecture, we will do molecularity and numericals on Arrhenius equation. The previous lecture was on collision theory, transition state, and Arrhenius equation. In the present lecture, we shall discuss molecularity of a reaction and solve some numerical based on Arrhenius equation as I told you. What is molecularity? A chemical reaction takes place due to the collision between the reacting species. A simple chemical reaction that takes place in one step is called elementary reaction. The number of ions, atoms, molecules taking part actively in an elementary reaction is called molecularity of the elementary reaction. The complex reaction is a combination of a multiple simultaneous elementary reaction, each having different reaction rate. Okay, and you know that the slowest elementary reaction is called the rate determining steps. You have seen this. The slowest elementary reaction is called the rate determining step. Next, the rate of the slowest elementary reaction is the effective rate of the complex reaction. The number of ions, atoms, molecules taking active part in the slowest elementary reaction is called the molecularity of a complex reaction. Please note down that. And the number of ions, atoms, molecules taking part actively in the slowest elementary reaction is called molecularity of the complex reaction. Now, molecularity is a whole number and can never be zero, negative or fraction, but order of reaction can be zero, can be negative, can be even fraction also. But molecularity is a whole number. It never be zero, negative or fraction. Example of simple reaction. H2O2 is giving you H2O plus half O2. Now the molecularity is 1. Okay, because one molecule. Now 2HI gas is giving you H2 plus I2. So the molecularity is 2 because there are 2 HI. And 2NO plus O2 is giving you 2NO2. Its molecularity is 3 because here 2 and here 1. So it is, the molecularity is 3. So if the molecularity is 1, it is known as unimolecular. If the molecularity is 2, it is known as the bimolecular. If molecularity is 3, it is known as trimolecular reaction. Okay. The reaction shown above all are simple reactions and involving only one elementary steps. In one step only the reaction is getting completed. Okay. So these all are the example of simple reactions. Example of complex reactions. 2NO plus 2H2 is giving you N2 plus 2H2. This is the reaction. Now this reaction proceeds in 2 steps. There is the step 1. First 2NO is reacting with 1 H2 and it is giving you N2 plus H2O2. And this is your slow reaction. That means this is the rate determining step. You will get the molecularity from this step only. Okay. Now, step 2, H2O2, which one we are getting here? That H2O2 is again reacting with another molecule of H2. It is giving you 2H2O. And altogether, I am getting 2NO plus H2 in the left hand side, that is NO plus this H2 plus H2, this is 2H2. You can add this to reaction. You will get the overall reaction. Okay. Now, step 1, being slower in the 2, it is the rate determining step, as I told you. The reaction correspond to step 1 involves how many molecules? You can see that it is 2 NO and 1 hydrogen. So, 3 molecules. See, step 1 involves 3 molecules of the reactants. Hence, the molecularity of the slowest elementary steps is 3, which is also taken as the molecularity of the overall complex reaction. So, for this particular reaction, the molecularity is 3. Am I clear? Some other examples of the complex reaction. 2FeCl3 plus 6Ki is giving you FeCl2 plus 6KCl plus I2. And 2KMnO4 plus 16HCl is giving you 2KCl plus 2MnCl2 plus 5Cl2 plus 8H2O. Now these reactions are complex as they do not take place in one step. On the contrary, a number of elementary steps take place simultaneously, resulting to the final product. Next, large number of reactants needed to collide. You can see for this one, this reaction, 2KMnO4 is reacting with 16 molecule of HCl. So, a large number of reactants needed to collide with each other for the reaction to take place in one step. This, however, is not feasible. So, maximum molecularity observed in an elementary process is 3. So, naturally, these reactions proceeds in several steps, several elementary steps. Now, see the difference between molecularity and order of reaction, and this is an important slide. So, please learn this. Okay, molecularity, it is defined as the number of molecules or atoms or ions participating in rate determining step. And order of reaction, order is defined as the sum of the powers of concentration terms in a rate equation. Now, molecularity is a theoretical quantity which can be determined through reaction mechanism. If you can write the reaction mechanism, you can say this is the molecularity of the reaction. But order of reaction, it is totally an experimental one. So, order of reaction can be determined experimentally. Molecularity is always a whole number or integer. It can never be fraction or 0. Order of reaction is 0, fraction, integer and whole number. Okay? Pseudo-unimolecular reaction. First order reaction having molecularity greater than 1 is called a pseudo-unimolecular reaction. If a first order reaction having molecularity greater than 1, so it is called pseudo-unimolecular reaction. A pseudo-unimolecular reaction is obtained when one of the reactant is present in large excess. The reaction is zero order with the respect to that reactant. The example, CH3COOC2H5 plus H2O. Now H2O is in large excess present, but that is the reactant. That is one of the reactant. Now, in an acidic medium, it is giving you CH3COOH plus C2H5OH. Now, the rate determining is done by K with only the concentration of CH3COOC2H5. We will not take H2O. That means it is present, but the concentration of H2O is not taken into consideration. So, the rate is K, the concentration of CH3COOC2H5, that is ethyl acetate. So, it is a first order reaction. Next, sucrose plus H2O. Now here also H2 is present in large excess. It is giving you glucose and fructose, but the rate determination is done by K concentration of sucrose. That is the rate of the reaction. Not taking H2O into consideration. That means this is also a first order reaction. So what it is said, the first order reaction having molecularity greater than 1 is called a pseudo-unimolecular reaction. But the molecularity is 2 here. See, CH3COOC2H5, the molecularity is 1 here, 1 molecule, and H2 1 molecule. So the molecularity is 2. In the second one also molecularity is 2. This is greater than 1. But the rate is, while calculating the rate, 1 is not taking place. So that is known as pseudo-unimolecular reaction. I think I am clear to you. Mechanism of a reaction. A reaction may be a net result of several elementary reactions. Already I told you. Each elementary process has its own molecularity and rate. Some elementary processes may be fast and some may be slow. The slowest elementary process is termed as rate determining step. All these 4 points you know. The fifth point, a sequence of intermediate steps or elementary processes proposed to account for the overall stoichiometry of the reaction is called the mechanism of the reaction. Mechanism of a reaction is elucidated based on experimental data. How to write the mechanism of the reaction? It will come through the experimental data only. Okay. Now let us see how to find out the mechanism of a reaction. Now here we have taken the example of the reaction between NO2 and F2. How to write the mechanism of this reaction? Now NO2 reacts with F2 to produce nitrile fluoride. See the reaction here. 2NO gas plus F2 gas is giving you 2NO2F gas. Now experiments reveal that the rate of the reaction is first order with respect to both NO2 and F2. This is experimentally we are getting it. Okay. So because you know that the order of a reaction we can get only through experiment. So the rate of the reaction, how to calculate? We have to know the order with respect to both the reactants. So we are getting that experimental data. It is showing that it is a first order reaction with respect to both NO2 and F2. So the rate can be written like this. First order rate is equals to KNO2 and F2. Now experiment also provide an existence of fluorine atom during the progress of the reaction. Since the rate law involves both NO2 and F2, one may conclude that the rate determining step is the initial reaction between NO2 and F2. And F is the transient intermediate. This F atom is instantly consumed in the next step, which is very fast. So, the mechanism for this reaction can be written as the step 1, NO2 is reacting with F2. It is giving you NO2F and one F is coming out. Now this F is the free radical. Now this F is reacting with again NO2, and as it is free, it will consume very fast. So we are getting NO2F. So now add these two reactions. So the sum of the two steps satisfy the stoichiometry of the reaction as follows. NO2 plus F2 is giving you NO2F plus F. Now NO2 plus F is giving you NO2F. Now just add it. This F and F gets cancelled. We are getting 2NO2. This means this 2NO2, because we are having 2NO2. This was my stoichiometry. 2NO2 plus F2 is giving you 2NO2F. We were started with this reaction only. We have started with this reaction only. So the stoichiometry, it is satisfying the stoichiometry also. So I can write the mechanism of this reaction like this. Is it okay? Now the molecularity is over. Some numericals based on Arrhenius equation. Question 1. If the rate constant of a reaction is 1.6 into 10 to the power minus 5 and 6.36 into 10 to the power minus 3 second minus 1 at 600 Kelvin and 700 Kelvin respectively. That means the two temperatures are given, and in these two temperatures the rate constant is also given. Calculate the energy of activation for the reaction. So my equation is log 10 K2 by K1 is equals to EA by 2.303 R 1 by T1 minus 1 by T2. This is the formula for the Arrhenius equation. Now just substitute the value. If you substitute the value, you don't know only the activation energy. And from here, you can get the activation energy. So this is coming 209.0 Kelvin Joule mole minus 1. Just write the formula and put the data in the formula. You'll get the answer. Now the slope of the line in the graph of log 10K, where K is the rate constant, versus 1 by T for the reaction is minus 5841 Kelvin. Calculate the energy of activation for this reaction where R is given. Now the slope of the line in the plot of log 10K versus 1 by T is coming, you can remember that it is coming the negative slope. So slope is equal to minus EA by 2.303 R. From there, EA is equals to 2.303 R into slope of the line. Now slope of the line is given, that is slope of the reaction is given, minus 5841. Okay, so minus 2.303, the value of R is given to you, and put the slope of the line graph and you will get the final answer for the activation energy. Third numerical, the rate constant of a first order reaction becomes 5 times when the temperature is raised from 350 Kelvin to 400 Kelvin. Calculate the activation energy for the reaction, and the gas constant is given. Now T1 is given and T2 is given, 350 and 400 Kelvin. Now K2 is equal to 5 times K1. It is given the rate constant of a first order reaction becomes 5 times when the temperature is raised. So naturally, in the first case, if the rate constant is K1, then K2 will be 5 times of K1. Rate constant is given. So the formula, write down the formula, log 10 K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2. Here you just put the value of K2 as 5K1. So K1 gets cancelled. So you can find out the value of log 10 5, and then all other things are known to you. You have to find out the energy of activation. Very easy sums. Only you have to put the data in the equation. Question number 4. In the Arrhenius equation for a certain reaction, the values of A and EA are given. 4 into 10 to the power 13 second minus 1, this is the value for A, and 98.6 is the value for EA. Now, if the reaction is of first order, at what temperature will its half-life period be 10 minutes? That means half-life, to complete the half of the reaction, the time period is given. That is 10 minutes. So you have to first convert it to second. So here they have changed it. T half is equal to 10 minutes, so 600 second. Now for a first order reaction, T half is equals to 0.693 by K. So from here, I can find out the value of K for the reaction. So the corresponding value of K is given by, this is 0.693 by T half. Now T half is equal to 600. So it is coming to 1.155 into 10 to the power minus 3 second minus 1. Second minus 1 because it is a first order reaction. So unit is second minus 1. Now according to Arrhenius equation, this is the equation for Arrhenius. K is equal to AE minus EA by RT. From there, take logarithm. So it is coming to log EK is equals to log EA minus EA by RT. Now take the 10 log 10. Log 10K is equal to log 10A minus EA by 2.303 RT. Now the value of K we are getting from here, and A is given 4 into 10 to the power 13 second minus 1. So we are getting the value of A also. It is given only in the question. Now the value of EA is given in kilojoule per mole. So that has to be converted to joule per mole. So 10 to the power 3 multiplied by, and then we are getting, put the value, everything is given to you, just put the value, only you don't know the T. So from there calculate the value of T. It is coming to 311.35 Kelvin. So this type of numericals are there for Arrhenius equation. Again I am repeating the same thing what I told to you, that copy all the questions in your notebook and try to do the numericals on your own. You have to practice the numericals. Now this is the end of lecture 5. In the next lecture, we shall study catalysis.